Welcome back, everybody. We are going to talk about epoxidation. Epoxidation of alkenes can be with MCPBA or a peroxide. And we are going to see how a non-regioselective and stereospecific, in particular syn-stereospecific reaction is going to affect alkenes. Here's an example of an alkene, and we'll start with this peroxide here. Let's do the mechanism of this reaction to understand, what's going on. This initial part is just going to be the epoxidation. So if you take this molecule and if you put a peroxide into it, it's going to go after the alkene. The sigma bonds are really not going to be affected by this peroxide. So to draw the peroxide, you would have acetic acid with an extra oxygen. Here is your acetic acid. And you will have an extra oxygen. Typically, there'll be a hydrogen here for acetic acid. You'll have one more oxygen here. So this double O right next to each other, that's the peroxide part. Okay, those are very, very reactive oxygens. And as you know, we put hydrogen peroxide to bleach out hair or the chromophores. And so that's pretty much what's happening here on a micro scale. So here is your electron-rich nucleophile. That's your pi. And because you have lots of oxygens pulling it, in this case, you can see some resonance here that's going to be tugging at these electrons. This oxygen is going to be electrophilic. Even though we have lone pairs on this oxygen, because it's of its proximity to this carboxylate, it's going to be electron deficient. So the first step, as usual, is going to be your nucleophile catching your electrophile. Those electrons then move over and break that sigma bond, form a pi bond, which is going to be too much for this. This all happens at the same time. It's a concerted reaction. And so concerted reactions have transition states, and we'll draw them next. And the pi bond pops out, picks up that hydrogen. And these electrons then go back over here and then go to the other carbon terminal. So you can see the pi bond literally picks up that oxygen, and that's it. So let's draw the transition state. As I said before, this is going to be a concerted reaction. Lots of things happening at the same time, and so we will have a transition state here. The sigma bonds again don't go anywhere. They're too strong to be broken by a peroxide. So your pi bond, as you can see, is breaking and reaching over to catch that oxygen. That oxygen has got a sigma bond that's breaking, and that is going to go and form a pi bond here between that carbon and oxygen, the carbon of the carbonyl. Now the sigma bond doesn't break on the carbonyl, but the pi bond breaks. And the pi bond then reaches out to this hydrogen, and the hydrogen is then pulled by this carbonyl oxygen. The CH3, of course, is just coming for the ride. And at the same time, these electrons are then pouring into this carbon. So we have a 5-membered ring and a 3-membered ring, kind of twisted up in the transition state. And that's just like a millisecond, a momentary thing in time. Now they all gel together and give you the actual bonds. And over here you have an oxygen bond on one side and another carbon-oxygen bond on the other side. These bonds have broken away, and you can see that the CH3CO is now a double bond on this side. This is gone and this is gone. So you sever it here and you form acetic acid, plain old acetic acid, salad dressing vinegar. So these are your two products. Now the way this reagent is, it can only add on one side. You can see it can't wrap around and add anti. So it is always going to be a syn addition. just because of the way the reagent is, and the mechanism would follow with, the reagent and the reactant structure. Now, this is syn addition. However, you are putting oxygen on both ends. There is no choice of whether it should go here or here. They're both equally, oxygenated. So it is non-regioselective. It's syn stereospecific. All right, and so that's going to be your product. Now, is there no regioselectivity at all? What they found was if you take the same molecule and you put a double bond right here, that double bond is going to be here and here for the most part, and this is going to be 86%. Your minor product would be epoxidizing this and this. That is your minor. So in that sense, it is regioselective. It goes for this over this. Why is that? If you take this reagent, you would see the only difference here is that this double bond has only one R group. So this is mono-substituted. Whereas if you take this pi bond, it's got two R groups flanking it. So it's di-substituted. And because it's di-substituted, there's a lot more donation of these sigma bonds into this pi bond. You know that these sigma bonds, when we had carbocations, they donate electrons. In a similar way, they donate electrons toward the pi when it is being pulled out by these peroxides. So these bonds come in the transition state. These bonds make a huge difference. Their donation pretty much swings the reaction in a way that it goes mostly here. So pi bonds, di-substituted pi bonds are more nucleophilic because they're electron rich. So this is your electron rich nucleophile. Now, of course, if you have tri and tetra-substituted, it's going to go even more. And so then here's your major that's going to be mostly on the di-substituted alkene and very little on the mono-substituted alkene. And you wouldn't form a product where you are epoxidizing this and not this. It's either both or this, and that's your major. Let's look at something else. We did E-butene and Z-butene with osmium tetroxide. Let's do it with MCPBA and see if we get the same thing. After all, they're both oxidations, right? Let's see what happens over here. So since we covered the mechanism here, we are not going to repeat it over here. I'm just going to show you the stereochemistry. So here's your MCPBA. It's going to put a oxygen right on top or bottom, either way. So let's say we put an oxygen right there. Now, this doesn't really rotate during the transition state. The entire time, there is a bit of a pi bond here, so there's no free rotation. So your methyl group is going to come out here, and your methyl group is going to go in here. And I'll just draw the hydrogens as well, just for good measure. So here is the epoxide. It's got two of these carbons that are very constrained because of the angle. It's got really large angle strain because it's a 60 degree. So it wants to really open up and go to a 109. How does it do that? Well, if you add things that are nucleophilic in here, they are going to pop open that bond because, as you can see, oxygen is going to be electron negative, delta negative, and these are delta positives. And because of that, there is a lot of strain here. And so we can relieve that by putting in nucleophiles in here. The most simple one is just water, and it can go at A or B. Let's say I have water here, H2O, and at A, it's going to attack here. At B, it'll attack here. I'm going to draw that again just to, make sure that you're following along. And here's your hydrogen here. Here's your trans methyl, and here is your epoxide as really polarized. these are electrophilic now. And so water can attack, let's say, at A or B equally, because there is no steric bias, because both of them have the same groups attached. So this rolls over and gets protonated. And I'm going to not draw that step. It just, it's very similar to what you did in SN2 and SN1. And so here, after protonation, you are going to get over here a OH2 that's going to get deprotonated by water again. And you will get a hydroxyl on the other side. But these groups on the side are going to remain the same throughout. And you will have a OH on this side. That again also gets protonated by water. So here your water is going to deprotonate this and protonate this, and it will give you a diol. Now these diols are on opposite sides. Let's look at what happens when you attack at B. So this is at A and this is at B. All right, let's look at this. So here your attack at B here, your water molecule comes in and attacks at B. And it's the same story all over again. It flips up that oxygen to relieve that really nasty ring strain. And now you have your methyl and your hydrogen in the same places. They don't go anywhere. And your hydroxyl is now going to form right here. So you'll have an OH2 which gets deprotonated, and the same water will protonate this. All right, let's look at this. What do you think is the relationship between these two? Are they mirror images? Are they the same? Or are they just, have no relationship to each other? So, all right, at first sight, these look like perfect enantiomers. But sometimes things can fool you. So always it's a good idea to make sure that they're not the same compound by rotating this and checking to see if they're actually enantiomers or if they're identical compounds or, any other relationship. It's always a good idea. Let's spin this around 180 degrees horizontally. Okay. So I made a model here. Your hydroxyl here is coming down, hydroxyl up, methyl over here, and hydrogen over here. And we can rotate it and draw it out like this. Let's draw this out when we rotate and see what happens. Over here, when you rotate this, then your methyl is going to come over here on the inside. Your hydrogen is going to come outside. Your hydrogen here is going to go inside, and your methyl is going to come up. So again, this configuration of trans is always maintained throughout when you start with a trans compound. The hydroxyls also, we just switch them around, and that is going to give you this molecule. Now, what's the relationship between this molecule and this molecule? Are they the same? Are they different? Are they enantiomers? What are they? What do you think? Can you take this and overlay it right on top? You can, right? Because they're exactly the same configuration. Methyl, hydrogen, hydroxyl in the same direction here and here. So these are identical compounds. Both of these are identical. So if you take this, this has a mirror plane of symmetry. And this has a mirror plane of symmetry if you rotate this and put the hydroxyls on the same side. Let me do that too. So here I'm going to take this and rotate this so that just one of the carbons here, and you would see that these are going to be exactly the same. This hydroxyl stays here. I'm just rotating this carbon here, and this hydroxyl then comes down, and you can see it's got a nice mirror plane of symmetry. So therefore, this is going to be achiral. Now, when you have achiral compounds and they have stereocenters, you can see this stereocenter has 4 different things, and this stereocenter has 4 different things, and there's an internal mirror plane. We have a special name for it. That's right, meso. So these are meso compounds. If you start with a trans butene, you'll get a meso. Let's see what happens when you start with a cis compound here. Are you going to get meso or enantiomers or same compound or whatever it is? Let's see what it is. So here is the same thing, and if you put your oxygen with the MCPBA, let's say you put it down. I'll draw the one that's down. Over here too, you can have the oxygen down and attack from above, and you would get the same compounds. I'm just going to draw this, out like this. So here's your methyl. Both of them are coming out this time because they started with a cis or a Z compound. Your hydrogens here, I didn't draw the hydrogens here, but they are going to be obviously the same as the methyl. Strands would be opposite, cis would be on the same side. We can do the same thing and attack with water on A and B sides. Let's say this is A and this is B. Let's see what happens when we open it up with water. Water can attack here. Water can do deprotonation. Water can do protonation. It's a very nice nucleophile, weak nucleophile, and a weak base. So I'm going to just show you that if you attack here, you're going to bring this down, open it up, and protonate it. So let's do that. And your methyl groups are going to be on the same side. They're not going to go anywhere because, as we said before, when you swing open, these configurations are preserved. After that, you can rotate it, but then the relative configurations are not going to change by rotation. And here are your hydrogens. Also, they're going to be on the same side. Now, your OH over here, oxygen swings down and gets protonated. Your water attacks up and then gets deprotonated. Now, this is going to happen on B as well. And we can also do the same thing with the oxygen up. And you will see, do it for good practice. Put the oxygen up and see, if whether you're going to get the same thing. You will get the same thing. So over here, you're going to attack at B. And your methyl and your hydrogen will be where it is. And this is going to be swinging down, and your hydroxyl from the water is going to be up. On the other end, again, methyl is going to be the same place as before. No changes there. Hydrogen is cis and methyl is cis. This will swing open when you attack it at B, and you would get your oxygen then getting protonated by the water molecule and giving you this. So A and B here are going to be what? Same compounds, enantiomers, diastereomers. Well, if you take this and put it on top, you know the hydroxyls are not going to be oriented in the right direction. If you place a mirror here, oh, well, it reflects perfectly here. Let's just for good measure take this and spin it around and see if you're going to get this molecule. So you can see, if let's say I take this, so you can see that the methyls are cis and the hydrogens are cis, and then you rotate them 180 degrees and you can see it's the same, it's a reflection of this. The methyls are coming on the opposite side now and the hydrogens are coming on the opposite side, and they're cis and it's still a reflection. So they are enantiomers no matter whether you look at it head on or rotate it and look at it. But just for good measure, I'm going to rotate B horizontally. When you do that, this is going to have your OH, the blue OH coming onto here, and the pink OH, which is the one that came from the original epoxide, that way we've drawn it, coming down. And the methyl group that are on a wedge are going to be now on a dash because we flipped them. And the hydrogens that are on a dash are going to become wedges. Going to come pointing toward you. And these methyl groups will be pointing away. Now what's the relationship with B? This is still B. I'm not going to put B prime. It's the same B. I just rotated it. So what's the relationship between this and this? Can we overlap them now? Even after we rotate, you can see they are non-superimposable because the methyls here are on dashes and here they are on wedges. Here they're going away from you. Here they're coming toward you. If I put a mirror here, does it reflect this? Yes, it does perfectly. So A and B here are enantiomers. And is there a preference for A or B? In other words, is there some enantioselectivity? If you look at this, the steric bias or the electronic bias for attacking A or B is identical. So there's no real preference for A or B attack. They're both exactly the same environment, sterically and electronically. Therefore, you'll have a one-to-one mixture of A and B. There's not stereoselective. However, you can only attack from the opposite side. So the formation here is syn, epoxidation. However, when you attack it, you're going to get anti-attack. Therefore, your hydroxyls are going to be on opposite sides. So it is stereospecific. It is not stereoselective. You get a one-to-one. You don't get, let's say, 5-2 or some ratio here. You get a one-to-one. So it's not stereoselective. It is stereospecific. You get anti-diol. Your oxygens when on opposite sides. So this is going to be a very typical example of a non-radioselective because you have equal opportunity attack here and here. But stereospecific, you formed a syn epoxide, then you opened it anti. In both cases, stereospecific. Now, we did see a similar situation before. We took trans and we put osmium tetroxide, and the trans gave enantiomers, and the cis gave meso. Do you remember that? The trans-butene gave enantiomers and the cis-butene gave meso. Why do you think there was a switch? Why is this opposite? That's because the osmium tetroxide didn't have an anti-attack following the syn attack. It was syn. So here we are doing a syn and then inverting it with the anti-attack. Therefore, these are switched around. Okay, so that's something to bear in mind. This way, you're not going to memorize these rules. It's very specific to the starting configuration. A certain stereoisomer would only give another specific stereoisomer. That is stereospecific. And we saw that earlier in our definitions. All right, guys, we will come back and do a few more examples with epoxide ring opening reactions. All right. I will see you soon. Bye.